Hello everybody and welcome back. I hope you had a pleasant time since I saw you last on Monday. If you remember, your homework was to finish the horizontal launch problems in the notes packet. So what this video is going to do is go over some of those problems. We can look at how to find the various known and unknown values and how to relate those to the equations that we know. Just some things to remember. We're using the exact same kinematics equations as last time. The only differences being the fact that we now have y and x because we have the x-axis, the horizontal, and the y-axis, the vertical, to deal with. And we have to think about acceleration in both the y and x and velocity in both the y and x. Remember, as we go through these problems, the horizontal axis can never affect the vertical axis. Anything in the x column of the t-chart has nothing to do with anything in the y column of the t-chart. In fact, there's only one variable that has to do with both the x and the y, and it's the only variable from our kinematic equations that represents a scalar. That would be time right here. Since time doesn't have a direction to it, it can't be linked to either the vertical or the horizontal. So let's do this problem. The first thing we want to do is analyze what we know. And for some of these classes, we did start this last time I saw you on Monday. In the following example, we've got a man standing on a 5-meter tall tower, and he throws a ball, and it lands 20 meters away from him. Right now, based on this, we can know some things right off the bat. For instance, we know that the x value in this particular situation has to be 20 meters because the ball travels 20 meters on the x direction, and the y value is 5 meters. Now remember, x and y are vectors, so technically, if we want to be really tricky about this, we could say that y here should be negative 5 meters because the ball is falling downwards. But for right now, we'll just leave it at 5 meters because, as you'll see, the math comes out pretty well either way. We can also see that, oh, see, I made a mistake. Hold on. There we go, that's better. I almost said that the velocity in the y direction was negative 9.81, which if I were there, you would all be making fun of me, I'm sure, because remember, acceleration in the y direction is negative 9.81. That's our gravity value right there. Because the ball is a projectile, as it goes through the air, gravity is the only thing that affects it, so we always know AY right there. We also know AX. More specifically, we know that AX equals 0. Gravity only affects things on the y-axis, things going vertically. Since we don't consider air resistance, that means anything going horizontally has no acceleration to it. This value will always be 0 for a projectile. No ifs, ands, or buts. Always, always 0. Finally, we also know that VIY must equal 0 meters per second. VIY stands for the initial velocity in the y direction. Before the person throws the ball while they're holding it in their hands, it has not yet started to drop. In the y direction, this is just like if you held the ball and dropped it straight down. It has an initial velocity of 0. So there are all of our known values from this problem. Quite a bit more than it looks like at the beginning. We've got an x of 20 and a y of 5. We know that ax equals 0 because it always equals 0 for projectiles. We know ay equals negative 9.81 because it always equals negative 9.1 for projectiles. And in this case, because it's horizontal, we know that VIY equals 0. If the ball were thrown upwards instead of being thrown horizontally, that wouldn't be true. But right now we're only doing horizontal launch problems, and if it's a horizontal launch, VIY equals 0. The last thing to do is see what it is we're trying to find in the problem, which we can see right up above. How long is the ball in the air? Which tells us that time is our unknown. That's what we've got to work with in this case. Time's what we're trying to find. So we need to have some sort of formula that has t, because t is what we're trying to find, and has in it ay, vi, and y, or a distance. In our kinematics equations, it might still look like x if you haven't copied it over into the new format yet. So something with t, a, vi, and y. We don't really care about this side of things yet because we don't have enough information to find t using our x values. If you're looking at your equations, and pause it, you can pause right now and take a look at them now if you need to. Hopefully you'll see that the equation is, drum roll please, ta-da, y equals vit plus 1/2 at squared. It's y instead of x because we're working vertically and not horizontally. And I kept the a in here, mostly because I forgot to switch it around, but some of you might have replaced this with g already, because remember, the a in this case is for gravity. So if we plug in what we know to this equation, pardon my handwriting here, we get 5 equals 1/2 times negative 9.81 times t squared. We can ignore the entire VIT section of this because VI is equal to 0. So VI times t makes that whole section go away. So we get the 1/2 AT squared. T is our unknown, so we can keep going on from this point. And that gives us negative 5 equals negative 4.905 t squared. Now the 4.905 comes from the 1/2 times the gravity, the negative 9.81. And I threw that negative on here in the 5 because we have our negative 5. Really what's going on is this object is falling downwards. So we can consider this 5 to be a negative 5. And if you want, you can put the negative here in the table as well. I probably should have done that from the beginning, so we'll do that right now. There, now we've got our negative in there. All that's left now is to divide both sides of this equation by 4.905. To cancel it out, that'll give us t squared. 1.02 equals t squared. And now we just take the square root of both sides to find out t, or how long the ball is in the air. We now see that time is equal to 1.01 seconds. Square root of 1.02 is about 1.01. So this is how long the ball is in the air. Now this took a long time to do, mostly because I'm trying to break out every single little step to this. Some of you probably have already finished this and moved on to some of the other problems. The next ones I'll go a little bit faster so you won't have to just listen to me doing nothing. At this point is an excellent time for the substitute to pause the video and see if anybody has any questions. You can rewind this and go over other parts, or quietly talk to your neighbors and see if they can help you at all. Once you've had a chance to talk, we'll move on now to the next slide. So the question here is, what if the ball is dropped instead? How long will the ball be in the air? And we still know a lot of these values. We still know that the x value is 20 and the y value is negative 5. VIY is still 0. AY is still negative 9.81. AX is still 0. The only difference is if the ball is dropped. Some of you picked up already that if the numbers haven't changed, then the answer we get isn't going to change either. That's because dropping an object on the y-axis is identical to throwing an object horizontally. On the x-axis, it's not. Throwing an object versus dropping an object. When you throw the object, it goes sideways, of course, and when you drop it, it goes straight down. But in either case, it's going to fall from the same height down to the ground. So the variables that we deal with are the same. So when we're solving for t, we already know that we're going to get the same answer, 1.01 seconds. We don't even have to do any math. If we did, it'd be the same equation all over again. Because when you're dropping an object, it is identical to when you're throwing it horizontally as far as the y-axis, the up and down, is concerned. So it's still just 1.01 seconds. Pause it here if you need to, ask questions or talk to your neighbors, and we'll move on. Now this next question is a little bit different. How fast is the ball being thrown? Let's take a look at that. First we'll put in what we know. There we go. It looks a lot nicer. We've got all of our information from before. And we know the time is 1.01 seconds now. Here the question is, how fast is the ball being thrown? Now, if it's being thrown, that means we're talking about our initial point of release. At the second it leaves this person's hand. And remember, he is throwing it horizontally. VIY is 0. So the second it's leaving his hand, all we're caring about is VIX. That's the only one that exists in that moment. So that is our unknown for this. Now the nice thing about this is if we're trying to find an unknown on the x side of the table here, because there's no acceleration in the x direction, there's only one x equation that we have to work with. It's so simple, I'm not even going to bother to type it. I'll let you see me do it right here. V equals change in x over change in t. That's it. That is the one and only x equation that we're ever going to use. So if we look at the x side of the table there, we see that we have change in x, that's this value. We see that v is our unknown, that's that value. And we have change in t, that's this guy right here. So if we plug in that information, we're going to get a pretty simple equation. Instead of v, we've got our question mark, so I guess I'll still just leave it v, I suppose, equals x, which is 20, divided by t, which is 1.01. And if you divide 20 by 1.01, you're going to get a number that looks a lot like 20, or v, velocity in the x direction, is equal to 19.8 meters per second, because it's the velocity that we're dealing with right now. So we know that vi in the x direction is 19.8 meters per second, which is about right. It took about 1 second for us to go 20 meters, so our answer should be about 20 meters a second, which is right in there with this. The x side will always be easy. You just have to remember to not try to solve it until you have more information, because a doesn't really exist, so you've got to have either x and v to find t, or like in this case, x and t to find v. What is the speed of the ball as it strikes the ground? Now this one's a little bit different. Let's take a look at what we know so far, all those same values from before. There's all of our information from the previous problems we've got laid out there, along with the addition of our VIX that we found in the last problem. What is the speed of the ball as it strikes the ground? So here's the ball right here. We want to know the overall speed as it hits. Right here it was traveling horizontally, so it was only the VIX to worry about because VIY didn't exist. There was an x component but no y component. However, at the end of its path, this ball actually has a diagonal vector representing its overall motion. Down here, there is, since it's diagonal, a y component and an x component. So we're going to treat these like two parts of a Pythagorean theorem. If you want to know the overall speed of something as it hits the ground, that one's a little more complicated because we have to combine this part and this part to make a resultant. Now we already know the VI because VI doesn't, or VX, pardon me, or no, the VX, because VX doesn't change. X is constant. But over here, it's not the VIY that we care about. It's the VFY that we care about, the final velocity in the y direction. So we've got to find this first so we can complete our Pythagorean theorem triangle right here. So if I'm trying to find that value, I need an equation that's going to have in it VF. And then I already have everything else. So I can pick whichever equation I want, basically. If you're anything like me, I tend to try to pick the easiest equation to use. So, since I already have all the pieces, VF equals VI plus AT seems to be the least work to solve this for me. If I plug in the information I have, VF is what I'm trying to find. VF equals VI, remember it's the y direction we're talking about, so here's my VI, 0 plus A, negative 9.81, times T, or 1.01. Plug all that math together, and I get VF equals, ignore the 0 right here, negative 9.81 times 1.01, or VF equals 9.91 meters per second. Strictly speaking, it's negative 9.91 meters per second because we are falling downwards. It's VF in the y direction after all. So this we can plug in right here. This is our overall y velocity. Now we've got our VFY right here. This is still not our answer. We want the overall speed of the ball as it strikes the ground. Remember, it's a vector. But now we do have the y component of the vector. That's a negative 9.91. And the x component of the vector, that's the 19.8 meters per second. So what we're really doing is we're drawing ourselves a nice triangle. There we go. So we've got the x component, and we've got the y component, and we're just going to use the Pythagorean theorem, or a squared plus b squared equals c squared. Once we do the math with the Pythagorean, here's our a, here's our b, although you could call this an a and this one b if you want. You'll get the same thing. A squared plus b squared equals c squared. So 19.8 squared plus negative 9.91 squared equals c squared. Work it all out, you get 490.25 equals c squared. Square root both sides, 22.14 meters per second equals c. This is the overall speed of the ground. So if you see it asking what is the speed of something, or what is the velocity, and it does not specify x or y, but just says speed, or just velocity, that's actually a sign that you have a more complicated problem on your hands, because you're going to have to take the x component and the y component and combine them to get that resultant overall speed. What about if we threw the ball twice as fast? How long would the ball be in the air? You'll notice my table's disappeared here because this is not actually a math question. It sounds like one, but it's not. It's not being thrown up in the air. So throwing it twice as fast only increases its x value for velocity. And as we know, the x values have nothing to do with the y values. They don't affect anything. So you could throw it twice as fast, 3 times as fast, 400 times as fast this direction, and still wouldn't change that it has to fall 5 meters with an acceleration of negative 9.81 meters per second squared, starting from a vertical velocity of 0. We're only changing the horizontal velocity. So the answer would still be that same 1.01 seconds, because we're still dropping it from the same height, regardless of how fast we throw it this way. If the ground at the far end of the field was sloped downward, would the ball be in the air for the same amount of time before it hits the ground? So what this is asking is, what if down here, this began to slope away? And my arrow can't go any further, it just kept on going down instead of being level. Would the ball be in the air for the same amount of time before it hits the ground? If you want, you can pause here. Everybody turn to your neighbor, make them go on record, tell you their prediction for this question. The answer is this time the ball would not be in the air for the same amount of time. It'd be in the air for longer because the ball is curving down. If the ground curves away from it, it will have to fall farther to hit the ground. This is basically how a satellite works. We have a planet like this, and around that planet we have a satellite traveling. A satellite is affected only by gravity, so it's a projectile. As it moves, it's always curving down, but the ground's always curving down away from it. So it just falls perpetually, always falling, but the ground always curving away from it as we go. The last question. A stealth bomber is flying straight ahead and level at 1250 meters above the ground at a velocity of 517 meters per second. How far ahead of his target on the x-axis will the bomber need to release his bombs in order to hit its target. So here we have a similar question. The stealth bomber is moving, let's see here, level. So that means it is horizontal as it's going. So this is a horizontal launch problem. 112.50 meters above the ground, so this is our y value. And this velocity is our VIX. VIX right there. We know it's only x because we're going horizontally. The VIY for this situation is going to be 0, because since we're traveling horizontally, it has not started to fall yet. How far ahead of the target will the bomber need to release its bombs in order to hit the target? Well, we need to see how long it takes the bombs to fall down this distance, and then see how long it takes the bomber to travel that distance when going at this speed. That tells us how far ahead on the x-axis we should drop things. So, let's take a look at what we know. We want to find, let's see here, I'll write this out for us. Here's what we know so far about this problem. So what I'm going to do is I'm going to find out how long it takes this bomb to fall to the ground. We know VIY, we know the y value for dropping, we know the acceleration, so we can find the time without too much trouble. Once I know the time, I know this particular speed, I know how far this plane travels in that amount of speed. I can use those to find out how far ahead the plane must drop its load. So, let's see here. If we want to find t, I've got vi and y and a. I'm going to use the equation we've used so many times before, y equals, in this case, VIY equals 0, so I can leave out the VI part and just say y equals, now here I would say VIY times t, but since VIY is 0, I can ignore it. So just 1/2 AT squared. And my handwriting on this is really terrible, so let me fix that for you. Let's see here. By using that equation, and I've left out the VI times t right here, I plug in the y value. 1/2 times a gives us that guy right there, times t squared. Divide both sides by 4.905, so this divided by that 4.905 gives me 254.8 equals t squared. Take the square root, t 15.96 seconds. The bomb will take 15.96 seconds to hit the ground. Now I have the velocity in the x direction and the time. To find x, I just need to see how much ground is covered in 15.96 seconds if you're traveling at 517 meters per second. I'm going to do that over here right now because the only equation for x is v equals x over t. If v is equal to x divided by t, v is 517, x is our unknown, t is 15.96. I multiply both sides by 15.96 to cancel it out. X is 8,251. The bomber must drop the package 8,251 meters before where it means for it to hit if it's going to land at the exact right spot. This is your lecture, or the rest of your lecture, on horizontally dropped projectiles, or horizontally launched projectiles. It is a complicated topic, but you'll soon see that every problem is really the same problem, just written as a man throwing a ball, or a bomber dropping a bomb, or a variety of other things. All the problems work the same way. For about 20 or so minutes now, I want you to work on these problems in your homework packet. Your homework packet has a significant number of horizontally launched projectile problems with your group members for either 20 minutes or as long as the substitute feels is appropriate. Work on solving those problems. After some time has gone by, we'll come back together and we'll talk some about things that are launched up into the air. Good luck!